What types of crops are best suited to synergy with photovoltaics and which should be excluded? Could there even be a situation where the high solar intensity hinder crop growth?
Yeah, this is a very important, relevant question for agrivoltaics. We know as agronomists and specialists of crops that different species can have different requirements in terms of radiation, but also have a shading, which is the reduced presence of radiation can have on the growth of certain plants. So some literature has recently reviewed the reaction, let's say, the suitability of crops to agrivoltaic conditions, and according to the reduction in solar radiation which is present under the plant, the crops can be grouped into three different categories. So there are some crops which are benefit from shading, or at least until a certain range, of course, of radiation reduction. And among these, for example, we have the berries like strawberries, blueberries, raspberries. So all the plants that typically have developed in the woods, so they are used to shade, but also some other crops like lettuce or some other crops that usually are find that direct radiation can be a problem. Then we have another group of plants which we consider shade tolerant, so which decrease their yield at increasing shading in a almost, let's say, direct proportion. So let's say that you have a decrease in radiation by 30%, you can have a 30% yield decrease. And there are some other plants which are susceptible to shading, which have a much more, let's say, steady and rapid decrease of yield at the decrease in available radiation. This is true in general, but it is also true that it is not just the plant and radiation that the type of plant and radiation that affect plant yield, but there are also other factors. So, for example, one important factor is water availability. So, for instance, in conditions where you have a high radiation intensity, like in summer, for example, and in particular you have low water availability because there is not much rain, there is no irrigation available, especially in windy condition and with dry air, in dry air. There is a lot of evapotranspiration requirement for the plants, and the presence of shade in this case could benefit the yield also for crops that normally would be susceptible to shading. Recently, there have been an increasing number of experimental evidences that prove this. So, for example, there are some research performed in the United States in which we see that forage crops can benefit from shading, especially when shading is present in the central period of the day. So at, let's say, around noon, midday, or especially in the early afternoon. And this is also interesting because opens the possibility not only of selecting the right crop for the agrivoltaics, but at the same time also to consider that agrivoltaics could be adjusted and managed in order to optimize crop yield.
What logistical and operation constraints to agriculture crops have to be compatible with photovoltaic systems? How can the irrigation system also be prepared?
Another important criteria to select the right crop for agrivoltaic, besides the suitability or the tolerance of the crop to shading condition is the mechanization of the crop. So the presence of the panels, beside projecting the shade, also create an impediment to the accessibility of the normal machineries that we use in agricultural production. So from the phase of soil preparation to the phase of planting of the crop, and especially to the phase of harvesting. Usually harvester for the most important crops is carried out by large machine like combine harvesters, for example. And the accessibility to the field of these big machines is often made very difficult or impossible by these machines. As a consequence, we have to consider that different type of agrivoltaic might enable the accessibility to the field to certain machines and not to others. So let's say that the decision on how to design agrivoltaics or which crop to choose for a specific agrivoltaic could be determined not just based on the suitability of the crop to the shading condition generated by the agrivoltaics, but also to the full set of machineries that are involved in the management of the crop. Among, let's say, the practices that we have in the management, in the cultivation of a crop, we also have irrigation, for example. So for sure, for an agrivoltaic, we cannot think about irrigating with large and big irrigation machines. Of course, was movement and also spread of the water in the field would be hampered or made impossible by the presence of the panel. So, for example, we have to choose different system of irrigation, like, for example, drip irrigation, which can be performed without big problems to any agrivoltaic conditions. Other, for example, machines which are usually quite large are the machines that are used to spray fertilizers or especially to spray herbicides or insecticides or other chemical products that can be used in conventional agricultural production. Usually these machines are quite broad and wide, and so they have to be somehow adjusted to the condition of the agrivoltaics. Another relevant aspect, which I think is often underlooked, is the fact that we have products that we spray in crops, both in conventional agriculture, but also in organic agriculture, which can, of course, have to be sprayed on the crop, but at the same time, in the presence of the panels, might be spread on the panels themselves. So these, of course, could interact with the durability of the panel, but also to the fact that some of this product, of course, being present then on the panel can reduce the energy conversion of the panel. So all these aspects, of course, have to be taken in due consideration when planning a cultivation under agrivoltaics.
What is the optimal range of proportion between agricultural area and photovoltaic area? And does this then vary depending on the type of the crops?
Yes. Let's say that I think this is a central issue that we also tackle in our research and experience in agrivoltaics. So the fact that usually we have specific, let's say, agrivoltaic technologies, and we want to see what is the best crop to a specific agrivoltaics technology. Or we have a certain crop and we want to see what is the best agrivoltaic technology for this specific crop. Actually, I think the best approach to design an agrivoltaic is to co-design these two aspects. So in a certain environment which has certain characteristics, as I said before, for example, in dry conditions or where is not present irrigations, then we have to consider that we have a set of crops that usually are grown, but thanks to the presence of agrivoltaics and its shadings, we might even be able to grow different crops. So the two problems should not be considered separately, but all together. And this, I think, is a very important aspect. It's important also, and we see in literature and in research that's been carried out on agrivoltaic, that what is considered a central issue in the definition of the concept itself of agrivoltaics is how much the agrivoltaic can reduce crop yield. So we all agree that agrivoltaics should be designed, optimized, and managed so that the crop produces an amount of biomass and product which is within certain limits of reduction compared to what it does in open field. So agrivoltaics is such normally when we install panels in the field where usually there is agriculture. So in Italy, for example, the norms say that an agrivoltaics is acceptable and is admissible, therefore, for construction if the agricultural activity can continue on at least 70% of the land which is occupied by the agrivoltaic system. In other countries, like in Germany, in France, or first in Japan, the norms, the government have set a minimum amount of, let's say, decrease in yield of the crops. So in Japan, for example, it is 20%. So if before you produce 100 with agrivoltaic, you cannot produce less than 80. And this number is 34% in Germany, or is even less in France. And as a consequence, one of the ideas or the objectives in the construction of the agrivoltaic system is to define, okay, but how many panels and therefore how much shade I can impose on a field or on a crop so that these limits are respected. So there was a recent publication from 2023 in which the crop yield was calculated through real data harvested in the field compared to the ground cover ratio. Ground cover ratio, basically, it's the ratio in between the number of square meters of panel present on square meter of land. So let's say if you have 5,000 square meters of panels per hectare, you have a 0.5 ground cover ratio. And so there is a relation in between, and you can see this in this graph, that there is a relation in between these two factors, and this can be taken as a kind of a well, we added this. It can be taken as a reference for the definition of how many panels to put per square meter. So, for example, the author of this work proposes that the ground cover ratio it cannot be above 25%, because this, on average, would enable the crop not to decrease yield by more than 20%. But we see in this graph that there is also a lot of variation, and this is due to the fact that the different crops react in a different way. So some crops, for example, increase their yield with shading. So why to, limit the presence of shading for this crop? So we are a little bit at the onset of the research on agrivoltaics. Of course, we know a lot about the biology of plant growth and its adaptability to the environment, but it's just like really few years that we are carrying out specific research on agrivoltaics. So for example, in my group, we have developed a mathematical model to simulate what is the behavior of a crop under agrivoltaics. And based on this simulation, we can make scenario analysis with different type of agrivoltaic systems, and also agrivoltaic systems that are varied in their design according to the ground cover ratio, so to the amount of panels. And then we see what is the effect or potential effect on yield. And based on this result of this scenario analysis, we choose the design of the agrivoltaic system, which optimizes our key performance indicator. And this is another important issue. So as I said, some governments have decided that agrivoltaics is acceptable if it does not reduce crop yield by a certain percentage. But crop yield and crop production is one of the ecosystem services which is provided by agriculture, but there are other factors. So, for example, there are other ecosystem services. So, for example, water use, but also the landscape value. So, some, for example, criticize agrivoltaics for ruining the landscape, and this is, of course, done in different ways or to a different extent by different agrivoltaic systems. Of course, economics are very important. So different agrivoltaics have different costs. So we also have to consider that we do agrivoltaics, and we consider agrivoltaics because we have to support the decarbonization of the energy production systems. And so decarbonization can be good because we need to decarbonize our system. But on the other side, we also have to have an energy system, a renewable energy system, which is economically viable, because of course our economy and our life depends also on the cost of energy. So there are a lot of trade-off that we have to consider when designing an agrivoltaic system. So an optimization based on a multi-criteria analysis is, I think, the best way to design an agrivoltaic system, and we are developing tools to do this.
Are there already any patterns or layout design for the arrangement of the panels as initial reference for an agri-photovoltaic project?
Yes, I think that the best is to distinguish two types of agrivoltaic systems. And the first, it was the DIN specification in Germany that distinguished the agrivoltaics category 1 to the category 2, which is more or less equivalent to what we have in Italy with the advanced agrivoltaics compared to the base agrivoltaics. And I think for this is quite useful to see also the graphical representation, which is provided in the DIN specification, in which as we can see, the agrivoltaics category 1 is the type of agrivoltaics that enable the cultivation under the panels. So usually these are characterized by different types of, let's say, design of the systems, but in all cases, the height of the panels from the ground is such that you can assess the soil with machineries, or you can walk under it and perform mechanical or hand operations. in Germany, but also in Italy. It's considered that the minimum height from the ground of category 1 or advanced, as we say in Italy, is 2.1 meter. In Italy, there is also the option where we have agrivoltaics combined to animal production, and in this case, the panels can be lower with a minimum height from the soil of 1.3 meters. The spatial arrangement of the panels, it can be very different. So these can be placed on structures with one axis or two axes, or they can also be fixed, but at a certain height, so the machine can pass under. And then we have the category 2 or base agrivoltaics, as we say in Italy, in which the cultivation of the crop is not possible under the panel, but just in between the array of the panels. So the machine can just pass in between the panel, which are usually supported by fixed or one monoaxial structure. There is also an interesting variant, which is the vertical agrivoltaics, which is in which the panels are bifacial and are vertical. So this creates, of course, a minimum amount of shading for the crops, quite simple structure as well. The drawback of this system is that, of course, they produce less energy per power of photovoltaics installed, because they are vertical, they are not oriented toward the sun, as most of the other actual systems, they are oriented north-south. And there is not a big development of the system, especially in the south, but they are quite popular in the north. So myself, I visited some plant, for example, in Denmark, within a project, a European project in which we are participating, but also in Sweden. And the advantage of this type of system is that they provide also a barrier to the wind. So they are like a break, they break the wind. And especially in this northern climate, where there is a lot of wind, which affects the growth of the crop, the presence of this barrier can be beneficial for the crop. And on the other side, the sun is also lower on the horizon at the north, and therefore this panel there also have a better energy yield compared than in the south.
How great could be the interesting potential for self-consumption for a farm? For example, in a pumping irrigation water, would it make sense if it happens during daylight hours?
I think that the use of energy on farm is a very relevant issue. And I think that the use of renewable energy, and in particular, or of a photovoltaic energy on farm, has been addressed by many in the past for exactly the same type of application, like pumping water, for example. That is quite common. Of course, the production of energy through agrivoltaics can address this energy need on farm. But I think that the impact that agrivoltaics can have on farm by far exceeds the energy demand of the farms. Actually, farms do not have very large energy needs. So the largest part of the energy need is really on farm, on traction, on mobility. So the use of, for example, tractors, which, okay, we can imagine that they can be electric in the future, but at the moment they are not. There are farms, for example, that need to store or cool store the products. In this case, they have a large fridge and they have a higher electric energy demands, and this can be an option, but often it's more the agro industry that needs energy more than the farm itself. While we see agrivoltaics as a let's say, large-scale production of energy. So when we think about an agrivoltaic plant, we don't consider a small plant of a few 100 kilowatt, but I think that wherever there is an interest for agrivoltaic in Europe, the idea is to have like a megawatt scale or 50 or 60 megawatt scale agrivoltaic plants. And in this case, the agrivoltaic plant is thought to produce energy for the community at large, so for the grid, rather than for the self-consumption of the farm. For example, in Italy, the Recovery Fund, besides promoting agrivoltaics, has also promoted the implementation of solar panel on infrastructure, like on stables, for example, or on buildings. And usually we see that these measures are limited to the demand, the consumption of energy by the farm. And the size of this plant is usually quite small. And this, I think, is also witnesses what is the size of the energy demands at the level of the farm. So it's interesting, but I think that when we think about the development of agrivoltaic, we think about large plants, which by far exceeds any energy demand at farm level.
Are orientable photovoltaic modules, such as the angle of inclination and up to the vertical position, for particular crops, or it's certainly a useful option for a larger scale for all possible crops?
As I said, there are different types of agrivoltaic systems. In most cases, I think that agrivoltaic systems are based on monoaxial structures. We have recently installed a biaxial agrivoltaics plant in our university, and if we see the cost of such a structure, which is very high because the axis is the main axis is about 5 meters, so there is really a very easy accessibility to the field. But by, of course, the price of these plants is very high, and maybe it's difficult to justify such a high price compared to the benefit which gives the agricultural production. Still, I think that monoaxial systems are quite relevant, and I'm still quite happy to have a biaxial system at my university because it's very flexible. By very flexible, I mean that this system can be and is normally conceived and used to maximize energy production per kilowatt of power installed, because of course the panel can track the movement of the sun completely, while with the monoaxial, of course, there is less flexibility in this sense. But you can also see it from another perspective, so from the plant perspective. So usually, as I said, the tracking system is there to track the movement of the sun, but it can also be moved, the panels, considering the radiation needs of the crop. And this is something that we are studying. And that's why I'm happy anyway to have a biaxial system in my university, because I can really move the panels according to my best interest, in the sense that it can be for the energy production, so I follow the sun, but it can also be for the crop interest. So I can, let's say, do an anti-tracking. So I put the panel in a different orientation so that it does not project shade, or the shade is really minimized. So as a plant physiologist, I have to understand when is the best moment to do this. But I can also consider this not just from the plant perspective in order to maximize yield, but also from an economical perspective. So we know that already now the price of energy varies during the day and during the year. So there will be a moment in the future, and it's already happened also now, where the price of energy will be very low or even negative. So at that point, it would not be a big problem to reduce the energy production, moving the panel in such a way that enables the crop to capture more light, particularly in phases in which the crop needs light. And each crop has particular phases of its crop cycle. So for example, around flowering, where it needs to, for example, have more fruits, in which it might be considered interesting to reduce a little bit energy production, but increase the yield potential of the crop. And other moment in which instead it's better to shade the crop to protect the crop from excessive radiation. And in that case, we also maximize energy production, because when we maximize shade, we also maximize light interception by the panel and energy production.
In the management of a photovoltaic system, for example, with the possibility of varying the angle of inclination of the panels, how should one reason from the economist point of view to benefit from the shading function to have an optimization of performance?
This is, ho appena risposto in realtà a questa domanda.
Infatti, la togliamo. Ok.
Sì, ma...
Sì,
Oppure
sì.
si può mettere a quella di prima, o magari ripeti la domanda in modo che...
Mi sono accorto, infatti, vabbè, ok. Bene, la ingolbiamo. Ok, riprendo dall'ottava allora. What technical challenge have been observed in the integration of photovoltaic system with the different crop types?
Anche questa direi che l'ho già risposta.
C'è già, ok.
Assolutamente.
Ok. Ok, partiamo con l'altra. How does agrivoltaic impact soil health, biodiversity, and the water use compared to the conventional farming?
This is an interesting point. I think, as I already said, we are in the infancy of studying agrivoltaics. There is a growing body of literature, which is growing exponentially in the last, I would say, 4 years. But most of this research has been focused on the impact of shading on crops. So how the panels influence the microclimate. So both the shading, but also the humidity, the wind, and the temperature, and how this affects crop yield. But it's also a fact that the presence of agrivoltaics can also affect soil health, for example. There is not much on this regard. We can make some hypotheses. So, for example, the shading can also be beneficial for the soil health, especially in dry climate where water is limited. Because, of course, where the soil is shaded, there is less evaporation of water, so the soil is more humid, is more moist, and of course, the presence of water in the soil is, let's say, beneficial for the life in the soil and therefore for soil health. On the other side, one of the major drivers of soil health, which is soil organic matter, can have a, let's say, a contrasting effect from the presence of the panels and shading. On one side, as I said, there is more humidity, so that is better also for the accumulation of soil organic matter. And the same for temperature, because the lower temperature means less mineralization of organic matter. So there is more conservation of soil organic matter. On the other side, the main driver of soil organic matter in the soil is the presence of biomass. So if we have a decrease in crop production, we also have a decrease in biomass, in roots. And this, of course, means that we have a lower input of biomass to the soil, and therefore less soil organic matter. So it's a very complex balance, but this has to be studied. Another aspect which I think has been tackled by many facing the optimal design of agrivoltaics is the possibility to plant under the panel a number of crops that can be, for example, more than crops, maybe species that can be, for example, useful for pollinators. And I think that in many projects which have been more focused to the mitigation of the presence of solar park, so more than agrivoltaics, they have been called ecovoltaic. So the fact that there were like solar parks that were not meant to be agrivoltaics, but still had to be managed, so to reduce the cost of management, because they have to be, of course, maintained, the grass have to be cut, they have to be kept anyway. The use of species that produce flowers which attract the pollinator can be good from the point of view, of course, of biodiversity, soil health, soil organic carbon in the soil. All these aspects can still be present in agrivoltaics in those areas in the agrivoltaic plant which are not cultivated by the crop. So, for example, if we take this category 2 or base agrivoltaic system in which we grow in between the rows of agrivoltaic panels, under the panel, when we cannot access with machines, then we can think about planting crops and species which have this benefit from an ecological point of view. So there are different possibilities to, let's say, maximize the value from an ecosystemic point of view of the agrivoltaics systems. È muto, sei muto.
What are the maintenance challenges unique to agrivoltaic system compared to standard photovoltaic installation?
Well, in reality, the agrivoltaic installation are not always very different from the standard photovoltaic installation, especially for the what we call the category 2 or base system, which are actually the same type of trackers, which are just a little bit more spaced, installed far apart to create more space for agricultural activity. The problem might be for the advanced systems, which are high up from the soil, and this, of course, creates a problem for the maintenance because you need more, dedicated machineries and apparatus for the maintenance. The main issue, I would say, which differentiate a normal photovoltaic power to an agrivoltaic power is the presence of the crop. Of course, when you have to do maintenance or cleaning of the system, you have the constraint of the presence of a crop. So these, of course, are not operations that are done, very often. So they are done on a yearly basis, and they have to be organized in consideration of the timing of agricultural operations. So, for example, you could do it after harvesting or after soil preparation or before soil preparation, rather than, of course, entering while there is a crop, as this, of course, would impact and squash the crop and lose yield. I don't think it's a big problem. It's just a matter of considering, the needs of the crop and organize this maintenance operation when the crop is not present in the soil.
What kind of training or education is necessary for farmers to successfully adopt and manage agrivoltaic system?
This is a very important issue. Until now, I think, and still we are in the process of defining agrivoltaics, optimizing agrivoltaics, studying what is the effect of the shading of the agrivoltaic and the change in microclimate and the agrivoltaic on crop performance. The farmer, of course, have to be trained. And I think part of the training is, and I think it's very important to consider security aspects. We don't have to forget that agrivoltaics infrastructure are not just an impediment, to the accessibility to the field with our normal machines, are not just obstacles, but are also part of apparatus which produce electricity. So there are, of course, safety issues that have to be taken into consideration, and all the norms and regulation that regulate photovoltaic park, of course, are also valid for agrivoltaics systems, and all these norms, of course, have to be respected in the first place for the access by a farmer to such a system. Another aspect is really to, I think, make the farmer part of the design of the agrivoltaic. And in my experience, I have to say that I studied agrivoltaics from the point of view of research, but I've been involved also on the design of agrivoltaic system in collaboration with companies, and I've been part also of working tables that have to define the regulation and norms. And really, my experience bring me to say that it's really relevant. It's not just a buzzword, co-design. In this case, it's really, I think, the key issue. It is not that farmers have to be trained to work in agrivoltaics. This is, of course, very important, but farmers are most importantly have to be involved in the process of designing the agrivoltaics, because the farmer know which are the machines. The machines can be adapted, of course. So, I mean, in the years, I think we have seen a progressive enlargement of the machine we use in the farm, because there are less and less, let's say, farmers, and the machine have to be bigger and bigger. So one single farmer can handle more land. In agrivoltaics, I think we have to go a little bit back. This, of course, means that it takes more space. It will be a little bit more expensive. We need more hours, but that is something which a farmer knows very well. So I think part of the training of the farmer can be, it's fundamental. It has to, of course, involve security, but it also has to involve aspects related, for example, to the management of the system. As I said before, it's possible that the movement of the panels can be the movement of the panel can be defined by the energy need, but also by the crop needs. And this most likely will be managed by algorithms that have to be informed by sensors, but also by farmers. So farmer has to be part of the process, know exactly which are the risks, which are the needs of the crop when grown under the agrivoltaics. And I think that one of the objectives, for example, also of our research, is to produce guidelines that have to be, I think, conceived also with farmers, and then have to be used by farmers to learn. The farmers have to be instructed on how to manage crops under agrivoltaics. That's a very relevant issue, as well as, of course, the electric sector and the technician of the electric sector have to be informed about the specificity of agrivoltaic systems.
What innovation in photovoltaic technology or agricultural practice could further enhance the effectiveness in the agrivoltaic system?
As I said, at this moment, most of the agrivoltaic systems that are being authorized or are in the process of being authorized are very similar to standard ground-based photovoltaic systems. There are some exceptions, of course, especially these overhead advanced category 1 agrivoltaic systems, which are just conceived to have the panels a little bit higher on the ground to facilitate the access to the land. There might be some innovation in these structures. Other innovation, I think, are related to the type of panels used. These, of course, would increase costs, which are, I think, it's very important to keep low. So most of the plant now use standard photovoltaic panels, which have decreased in price enormously in the last years, and this is a trend which continues to go down. But there are also on the market different systems, for example, which have a different permeability to light. So, for example, we can have panels that let more light pass, either because the cells are more spaced on the panel, or because the technology uses selective panels that let the share of the radiation, the part of the radiation which is more useful for the crop, pass to the crop. So these are type of innovation that we can imagine. I think that what is very important, and we are working on that, is to work on the monitoring of the agrivoltaic system. Every photovoltaic park has a very efficient monitoring system. So who manages a photovoltaic park has real-time information about the energy production, any type of problem, any aspect which is of interest for the management of the photovoltaic part, continuously monitor it all the time. The same has to be available also for the agricultural part. So we are installing, for example, different type of sensors to monitor the crop, to monitor some parameters which are relevant for crop growth. So, for example, water content in the soil. I think it's very relevant to monitor phenology. Phenology is the determination of the state of advancement of the crop in its cycle. As I said before, there are moments in which the crop might have more needs in terms of radiation, and therefore we need to know if the crop is at this stage. So there are different sensors that can be used for this purpose, or to know if the crop is stressed, and therefore maybe to change the direction of the panels to help the plant, or simply apply irrigation, which is what we do normally. I think that the realization of a multi-sensors platform connected through IoT, it's a relevant implementation that has to be conceived for agrivoltaic systems to improve the management of the crop. In Italy, for example, this is compulsory for a certain type of agrivoltaic system which are financed by the recovery fund, which have a special type of monitoring. But in general, all agrivoltaic plants have to be monitored in order to provide the information that prove that actually the agrivoltaics is an agrivoltaic. Because one of the main concern, I think, of the government, but also of the public, is that agrivoltaic are not an excuse for placing photovoltaic panel in the field where it costs less and it's very easy. And in that case, it will be a kind of a greenwashing. So that is a concern that is quite widespread. throughout the population, but especially in the agricultural sector, and the proper monitoring of the crop, not only to, of course, inform the management of the crop, but also to inform, you know, the regulatory body that actually the crop was grown under the agrivoltaic and the performance of this crop is satisfactory for what the norm say and enforce.
And now, what are the main barriers to the widespread adoption of agrivoltaics, and how can this be overcome?
Well, I think that this is a good last question, because everything we said so far is a piece of a complex puzzle, which is the design of optimized agrivoltaic systems. It's very complex. Our complex systems. Of course, everybody understands that there is an electric part, a photovoltaic part, and an agricultural part that by themselves are already quite complex. Putting them together makes it even more complex, also because it's not just a simple linear addition of two systems, but there are a lot of complex non-linear interactions which involve the combination of the two systems, and by itself the agricultural system is totally non-linear, so it's very complex. Usually when you have a complex system, you try to solve the part of the system which is more known, which is the photovoltaic system. So I think so far the agrivoltaic system has been managed more from a photovoltaic part than from an agricultural part. And as I repeatedly said, I think it's very relevant that in the design and optimization of the systems, there is a co-design. So at least the agricultural part is involved, but I think it's even better if all the stakeholders are involved in the definition of what is an acceptable agrivoltaic system. And I think in the end, this is the real key issue in the expansion of agrivoltaics, is social acceptability. We see in Italy that we needed to do decarbonization. We have very clear targets, which are very high, and in a very short time, by 2030, we have to more than double our photovoltaic installations. Most of this has to be done through agrivoltaics, because for sure, maybe half of it will be done through integration of photovoltaic panel to the infrastructures, but we don't have so many, infrastructure and not well rented over south, and then the cost is much higher than to have ground-based system. So that is a way forward for the decarbonization. We have to do it, but we are not moving very fast, and the main reason is that at the centralized level, we say, okay, agrivoltaics is a good solution, but then at the local level, we have a lot of difficulties from local government and local population that do not want, the agrivoltaics is the usual, not in my backyard problem. So solve this. I think that we have to show that agrivoltaics it's feasible, it's intelligent, and they can be designed in such a way to provide benefit for the community and also for the agriculture. For example, we have a project in which is actually financed by the Regione Emilia-Romagna, in which the objective is to study and optimize and collect information on agrivoltaics, but with purpose of decarbonizing the agro industry. So our first step, I think, it could be to see the agrivoltaics as an opportunity for the agricultural sector and agri-industrial sector. Agri-industrial sectors has an impact, an energy need. So if the energy needs of the industries are at least partially satisfied by agrivoltaics, it could be an evident benefit for the industry and for the you know, both from an economic point of view, but also from an environmental and social point of view, because the, let's say, carbon footprint of our agricultural product would be reduced through the implementation of agrivoltaic. This is a first step. Maybe it's too short as a step, considering the long path we have to go in a very short time for the decarbonization of society and industrial production in general. But that could be a good starting point.